The Gauss-Jordan algorithm. This is very exciting. So we just saw in the last lecture that we care about solving linear systems of equations. And if the system we're studying is in reduced row echelon form, then there's a systematic procedure for writing down all solutions to the system. Of course, the problem is that if we come across a system of equations in the wild, it is almost guaranteed to not be in reduced row echelon form. So how do we take something that's ugly, not in reduced row echelon form, and turn it into something that's nice, meaning in reduced row echelon form? Well, the Gauss-Jordan algorithm is exactly the tool for the job. So let's discuss Gauss-Jordan elimination. So the first thing to learn is that there are three types of elementary row operations. The first type is called row switching, and this says that if we are working in this way, we can simply take two rows and switch them, and that's the first type of elementary row operation. The notation we use to indicate that we are switching the ith row with the jth row is sort of vector r sub I and then a double arrow vector r sub j. The next type of elementary row operation is called row scaling. Here, the idea is that we can take any row, so we can take maybe the ith row, and then we can scale by any non-zero number. So the notation we use for this is we write scalar times the ith row, so vector r sub I, and then we write right arrow r sub I to indicate that the new ith row is obtained by scaling the old ith row by the non-zero number c. And the third type of elementary row operation is called row addition. Here, the idea is that we can take one of the rows, maybe row I, and then add a scalar multiple of another row, maybe row j. So the notation here says we can take the ith row, so vector r sub I, and then add any scalar multiple c times the jth row to the ith row, and then send that to the new ith row. So the new ith row is obtained by taking the old ith row and then adding c times the old jth row, which is the same as the new jth row because the jth row here is not changed by the procedure. Okay, so let's see these examples, or some examples of this in action. So here what we're going to do is we're going to take this perfectly good 3x4 matrix, and we're going to perform a row switch. We're going to take the first row and switch it with the third row. So how does that work? Well, we have our first and third rows, and then when we do the elementary row operation, we switch the first and third rows. It's that simple. What about row scaling? So here we're going to take this perfectly good 3x2 matrix, and this notation says we should take the second row and then scale it by -3. So here's the second row. Let's perform the row operation by scaling it by -3. So we take the original -5, -7. When we multiply by -3, we produce the new row 15, 21. Finally, for row addition, the example here is a little larger. Here we're taking this 4x5 matrix, and we're going to do the operation where we take the third row and subtract 4 times the first row from it, and then that becomes the new third row. So here's the third row of our matrix. And now the idea is that I'm going to take this row and then subtract off 4 times the first row. So the first row is right here. So how does the arithmetic work? Well, I'm going to take apparently -1 and then subtract 4 times 2, so that's -1 times 8. That becomes -9. Then I do the same thing for all of the other coordinates in the third row here. So these are the three types of elementary row operation: row switching, row scaling, and row addition. Okay, so the idea now is that if we have something ugly, some generic matrix that's hard to work with, we will use elementary row operations to make the matrix better. So it turns out there's a theorem that says we can do this. Every matrix A can be row reduced to one and only one reduced row echelon form matrix. So let's see an example of this in action. we will present an algorithm for doing this, so a systematic list of procedures for taking a matrix and then doing row operations to get to reduced row echelon form. But for now, I just want us to think about the idea. What would we do if we wanted to get from something not in reduced row echelon form to something in reduced row echelon form? So here we have a perfectly good 2 by 3 matrix, but it's clearly not in reduced row echelon form. Well, what's the problem? Well, if we look at the first row, the first entry is not a pivot because in reduced row echelon form, we need this entry to equal 1. So let's fix the problem by using a row operation. How about we take that row, so the problem here is the -9. Let's take that whole first row and scale by -1/9. So if we multiply the entire first row by -1/9, the -9 becomes a 1 now, the 18 becomes a -2, and the 20 becomes -20/9. So we're actually a little bit closer to reduced row echelon form because now we have a pivot. This first entry is equal to a 1, so that can be our first pivot in our reduced row echelon form. Of course, we're not there yet because another axiom for reduced row echelon form says wherever we have a pivot, we have to have all zeros in the column except for the pivot. So of course the issue now is that right below my pivot, I have this -5. Well, I want to get rid of this -5, and if you think of the row operations available to us, only one will do it. So we can't do a row switch to get rid of the -5. That would mess with the pivot that we just worked so hard to get. I can't do a row scaling to get rid of the -5. It's tempting to just multiply this entire row by 0, but remember, for row scaling, we're not allowed to scale by 0. So the only thing left is row addition, and the general principle says, if you're trying to get rid of entries in a pivot column, take advantage of the pivot. So here, what we really want to do is we want to manipulate row 2 using row 1. And the right way to do this is to take row 2 and add 5 times row 1. So now let's do that. So what is row 2 plus 5 times row 1? Well, now we know that we'll get a 0 in the 2, 1 position. And then we have 10 plus 5 times -2. That's also 0. And then if we do the fractional arithmetic, we'll take 11 and then add 10 times -20/9. And that ends up giving us -1/9. So we have successfully eliminated the entry right below our first pivot. And so now that entry is okay. Great. So we're doing a pretty good job. We're a lot closer to reduced row echelon form than when we started, but we're still not there. We have our first pivot, and the column is now legit. The only other entry is a 0, so we're done with our first pivot column. Now we ask ourselves, well, where might the next pivot be? And the only possible position would be in this 2, 3 position where we have a -1/9. Well, remember, in reduced row echelon form, pivots have to equal 1. So how can we take this -1/9 and make it a 1? Well, we can use row scaling. We can multiply the second row by -9, and that produces a 1 in the 2, 3 position. That will be our next pivot. So now we're a lot closer to reduced row echelon form. I now have 2 pivots, but I'm not quite there because right above my second pivot is -20/9. I need to get rid of that -20/9 in order to be in reduced row echelon form. And here we can use row addition. What we want to do is we want to take row 1 and then subtract off -20/9 times row 2. So that's the same thing as taking row 1 and adding 20/9 times row 2 to it. When we do that, we successfully get rid of the non-zero entry above our second pivot, and we have a 0. And now if we stare at where we're at, we realize this at this stage, we are in reduced row echelon form. So we've successfully found what's called RREF of A. We started with a 2 by 3 matrix that was not in reduced row echelon form, and we carefully chose row reductions until we ended up in reduced row echelon form.